Hello, everyone. Welcome to another Enamines webinar. Pleased to see you all, to have you all here. So we have a lot of things to share today, so let's keep going and let's start the show. Before we start, I would like to tell you how we will be working today and how all of this will be happening. So, a few words about the rules of the webinar. The first things first, the webinar is being recorded, but don't you worry, being recorded only what's on the screen and the speakers themselves. So, and since it is recorded, it would be distributed on our YouTube channel later today. So in case your colleagues couldn't make it today, don't you worry. You can share the link and the webinar will be there forever. Uh, all the participants will be muted during all the time of the webinar. And if you have any questions, feel free to put them in the question box. It's down below on the screen at the right-hand side of the bottom. And yeah, please stay tuned to our news and what's going on at Enamine and follow us in social media. In all of them, we are there. The webinar will consist of three parts. So first of all, I'll give a brief introduction of what's new. The second part will be our key speaker, and the third part is actually the Q&A session where basically we will be answering the question whatsoever. So if everything is well spotted, so let's get rolling. So a few words to remind what is Enamine and where we are, what we are. We are a contract research organization of 35 years of history. For now, we are located in six different countries, and our headquarters are in Kiev, Ukraine. And the very interesting thing that we have the largest amounts of chemists in Europe in one place, more than 700 of those. Um, we we are a unicorn in terms of because we are the largest producer of chemical building blocks and screening compounds, as well as we are a contract research organization. We have a biology services. We have basically we can do everything starting from the catalog and into the deliver your research, deliver your project up to before the preclinical studies. And yeah, we are 100% service oriented and we do not have our own drug research. Um, and as I have mentioned that we have 35 years of our history and it's our 35th anniversary. And what's a birthday without a party? And we will be having one of those. And later this year, in September, we will be having a major 4-day event in Europe, in Riga, Latvia. It's called Enamine Drug Discovery Conference. And yeah, this meeting is a full-time conference having scientists from organic chemistry, medicinal chemistry, computer science, and as well as biology under one roof, let's say under one team for 4 days. Yeah, and every one of you are very welcome to come to Riga later this year. It's a fantastic European city, and it's worth visiting if you haven't been there. We will be in a fantastic, very nice hotel. We will be having a keynote speaker. We will be having top speakers in the fields that I've just mentioned. Um, they're world renowned names, and all of the information about the conference you can find on the Enamine conference.org. And if you have any questions, yeah, just let us know and we will be happy to answer them all. So registration is all open, and the early bird actually expires in a couple of days. So uh, make it as quick as possible to save up to 40% from the tickets. Yeah. Yeah. So let's get back to the scientific part and to tell you more about our compounds and building blocks. So, as you know, Enamine is the world's largest supplier of chemical building blocks, and we have almost like more than 70% of the world's stock. And here you can see the growth by this orange line year by year from 2010 of this 15 years of substantial enlarging of the number of the building in stock building blocks, and we are keep evolving. And today we will be covering mostly the building blocks, and with myself and the other speaker, Yevgen, we will. And before giving the word to him, I want to say that building blocks that we have at Enamine are they cover huge chemical space, and they might be used in different research areas. And for example, when scientists know precisely what they are seeking for and what they want to purchase, they just go to the web shop and paste the ID or smiles or other identificator and purchase the compounds. But sometimes scientists want to know the scope of the fields, and that's why we're working really hard to slice our catalog to make it as searchable as possible, as easy to search and navigate. And that's why in a couple of slides, I want to highlight a new classification that our teammates from Enamine have been working hard to extract and to slice the catalog for a better navigation. Just in few words, because every single topic that I will be covering next requires an additional webinar, and we will be happy to have all of them in place eventually here online. But yeah, it's a work in progress. So first, it's the active pharmaceutical ingredients. We have categorized some of those. This includes the APIs themselves, the impurities, and nitrosamines. Yeah, they're all searchable, and yeah, you always need some research need them to find out what's the impurity, to find out what's the other stuff to have. Other stuff that we've freshly brewed and freshly categorized is bioarsenal reagents. Uh, that includes actually the tetrazines, the uh, cyclooctanols, and this trans cyclooctanes. Yeah, they're suitable for a strain promoted azide-alkyne cycloaddition. Yeah, fantastic area to be in. Other stuff, which is like all the organic chemists are well off, is catalysts and ligands to the catalysts. Yeah, we're working hard. We have a great group of 20 people who are dedicated in only this direction. And actually, we had a webinar dedicated to catalysts and ligands, and this includes a fraction of world known part of the fields, as well as we are having our own research group that's working in this field every single day. The DNA-encoded libraries is a very hot topic. It's going for 10 or so years, and we are in it because we do have a bifunctional DEL-compatible scaffold and trifunctional scaffolds as well. And this is a very good starting point in your DEL project or a follow-up of those. Isotope labeled compounds, we also do have them. Sometimes this include the labeled drug substance, that's well-known drug molecules, and also the building blocks themselves. Sometimes you really need to know to identify where the molecule is going, and it's probably the cleanest option to do that for this purpose. It's linkers. And this is connected with the product story. I hope you're well aware of it. And we also have another big group, and I hope we will be having another webinar, the next webinar dedicated for this topic. Yeah, we have a fantastic selection of these building blocks that are bifunctional and protected with FMOC and BOC groups. Yeah, the distance and the flexibility of the compounds depends on the linker itself, on the molecule. Metal organic, covalent, and hydrogen bond organic frameworks. We also do have them as well. This is mostly connected to the material science, but nevertheless, it might be used and applied to these types of compounds in other research areas. Another fantastic product that we have is basicity tuning kits. These are sets of compounds from 7 to 15 compounds. They are already in the box and ready to ship. So this is a very cool story when you can play with the basicity with the pKa range, starting from 2.5 ending up to 12. So it's a fantastic ready to use product that just waits for your research to be tuned. Connected to this story is also freshly made late stage functional kits, but in a slightly different sauce. Very cool stuff. Yeah. Just been on the website, I don't know, for a month or less. So it's a fresh product, super fresh. Also, as you know, we have a huge enamine bioactive compounds. It's another project that we have, and another group, another team that's dedicated to this project. And also, we are partnering with a big pharma company, and we are the authorized seller of Pfizer compounds. And this is the library of about up to 300 compounds, or a bit less. And these are ready to ship well-known bioactive compounds of Pfizer. And yes, we are happy to have this collaboration in place. So, and that's probably the last but not least. And all the information that I've been just highlighting, it can be found more in the more details on the website, because we are highlighting on the information on enamine.net, and we are highlighting it the new, and you can find out more on the information on each topic. And basically, eventually you can purchase them on Enamine store, and we have the categories for all of the just mentioned stuff from my side. Yeah, so I think that would be it from me, and I will be passing the words to our speaker, Dr. Yevgen Ivan. He graduated from Taras Shevchenko National University, received his PhD there 5 years ago, and he's a passionate synthetic chemist as myself, and he worked many years in the lab. And starting almost 5 years from now, he is a production manager at Enamine, and he mostly focused in this recently focused more and more in the compounds for photoaffinity labeling. And yeah, so that's the main speaker at today's webinar. And please welcome our speaker, and I will be stop sharing my screen and pass the word to Yevgen. Yeah, Yevgen, the floor is yours.
Thank you, Alexey, for introduction. Dear guests, hello. Let me share my screen. Let's begin. I'm sure that many of you guests are familiar with the topic of photoaffinity labeling, PAL, but it wouldn't hurt to talk a minute about some basics. So, medicinal chemists, among all other problems, often have two tasks. First, to identify and validate target biomolecules which are affected by our studied molecule. And the second task is to identify off-target interactions. And both goals are not easy to achieve because such interactions often are dynamic, and we need a special tool which can allow us to capture that dynamic interactions. And photoaffinity labeling is that tool. If you allow, I simplify a PAL experiment scheme. So at first we should create a photoaffinity probe. What is the probe? The probe is a molecule which is based on our studied molecule with additional photosensitive group. We should keep the structure of a probe so close to the parent studied molecule as it possible, because we want to keep the binding ability of our probe in comparison to our studied molecule. Let's imagine that we have already designed and synthesized the probe. Then we can incubate it inside a cell, irradiate with light, typically in ultraviolet range, and during this irradiation, some active particles are generated. That active particles can include carbines, nitrines, radicals, diazoalkanes, etc., depending on the structure of photosensitive group. And these active particles can form covalent bonds with neighboring biomolecules, which are close to them in space. And that covalent bond is the key that allows us to capture and to analyze obtained adducts. In general, photoaffinity probe consists of three main parts. First, it's the scaffold of our studied molecule, which is decorated with two additional groups. First group is tag or click functional group, which is essential for purification and for enrichment of adducts after experiment. And second is photosensitive group. And photosensitive group is the topic of our today's webinar. It should be mentioned that in general, not always, but often, such probes can be constructed in modular way by adding tag and photosensitive group to our molecule of interest. Let's go over photosensitive groups. At the screen, you can see some widely used classes of organic compounds which can be utilized for photoaffinity labeling. The list includes benzophenols, arylazides, diazirines, aryl tetrazoles, oxodiazolines, and other compounds. The list isn't finite because each year chemist develops new classes which can be used for PAL. But today we are speaking about those compounds which have already been used. So each class, according to its structure, can generate active particles, the radicals, nitrines, carbines, etc., during irradiation with specific UV wavelengths. And each class has their own advantages and drawbacks. Let's go over class by class. Let's start from some historically important compounds. Those are benzophenols and arylazides. Benzophenols now are rarely used as an additional blocks for PAL because of their bulky size. Nevertheless, those compounds are readily converted in reversible manner to diradicals during irradiation with long waves. And there are several cases in which benzophenols can be used and are used. First of all, benzophenone can be the fragment of your studied molecule, and you can use it as a photosensitive group. And second, benzophenols as an additional blocks can be used for PAL when you are studying big molecules. For example, when you are studying protein-protein interactions. Those compounds are easily accessible. We have several hundreds of them, and some representative examples you can see at the screen. Next, arylazides. Arylazides are smaller compounds, and in the case your studied molecule have arylurin inside its structure, formal additional of 3 nitrogen atoms is the smallest possible intervention to its structure. So arylazides are comparable small compounds, but they need short wavelengths of irradiation to be activated. And this range typically lies between 250 and 290 nanometers, which is harsh UV light, and it can be damaged for cells. Nevertheless, they are used And these compounds are also widely available, and we have half of a thousand of different functionalized aryl azides, and some examples which were specially designed for PAL you can see at the screen. Let's go next. We also have some newer classes of compounds, such as aryl tetrazoles and oxadiazolines. Both classes are smaller, comparable to benzophenones, and both classes need longer wavelengths of irradiation to be activated. So we also have such compounds and we can use them. Next class is the most important because diazirines are the most popular compounds for PAL now because of the big list of their advantages. Those compounds are stable, they are excited at near UV range, about 350 and sometimes to 380 nanometers. The process is irreversible, fast, and the compounds can be really small. And we have several hundreds of different diazirine building blocks, specially designed for photoaffinity labeling. Let's divide them into several categories for convenience. First, let's talk about aryl trifluoromethyl diazirines. Aryl, aryl diazirines are among first compounds which were used for photoaffinity labeling, but ordinary aryl diazirines without perfluoroalkyl group tend to form carbenes known as diazoalkanes, and diazoalkanes can be responsible for background labeling and for false labeling. And to avoid this problem, aryl trifluoromethyl diazirines has been developed. And additional of trifluoromethyl group reduces reactivity of corresponding diazoalkane. So we have just labeling by carbene pathway only. And we have all necessary building blocks based on aryl trifluoromethyl diazirines with all common functional groups with different substitution pattern. So those compounds are good, but they still have one drawback, it's their size. And to overcome issue of size, let's go to smaller compounds, to aliphatic diazirines. Aliphatic diazirines include terminal compounds, 3H diazirines, and dialkyl diazirines, often 3-methyl 3-alkyl diazirines. Terminal compounds are the smallest possible. We have them, but they need shorter UV range to be activated. And dialkyl diazirines, for example, 3-methyl 3-alkyl diazirines, are also small compounds, but they need longer UV wavelengths to be activated. And we have a big collection of monofunctionalized dialkyl diazirines. And we are proud with this collection. We have 100 of such compound, and you can see some relevant examples. Some of those compounds are unique. For example, the smallest possible compounds like alcohol 30, bromide 31, carboxylic acid 32 are the smallest possible monofunctionalized 3-alkyl diazirines. And those compounds have been developed by our chemist and are supplied by Enamine only. Also, we have some their well-known homologues. You can see them at the second row. And also we have some special cases. For example, there are several recent research papers made by scientists from United States, and it has been shown in those papers that some spirocyclic diazirines, especially cyclobutane-based diazirines, show enhanced reactivity. So you can use spirocyclic diazirines when you want to increase the reactivity of your probe. Let's go next. Next, compounds are fully functionalized diazirines. Let me remind that at the beginning of the presentation, I told that we need two additional groups to create a photoprobe, quick functional group and photosensitive group. And we can combine them inside one unit. And that one unit, with an additional ordinary functional group which is used for connection, is the fully functionalized compound. So, fully functionalized compound is one unit which is created for convenience those compounds are ready to use, and you can create your probe or your some fragment libraries based on those compounds just in several simple synthetical steps. So we have a wide range of fully functionalized compounds. For example, we offer some well-known minimalist diazirines like compounds 50 and 51 with different functional groups. We have next generation smaller compounds like compound 52 or 53. We also have some special cases, for example, cyclobutane-based spirocyclic diazirines with enhanced reactivity like compounds 54, 55, and 56 with different functional groups. And we even have a diazirine containing fully functionalized amino acid in different forms. So you can use these compounds and add them to your studied molecule in several simple synthetical steps. And let's go to the last group of diazirine building blocks. This group includes amino acids, and we have some isosters of natural amino acids, such as photoleucine, photomethionine, photoproline, and photophenylalanine. All those compounds have similar structure to natural amino acids, and they can be incorporated into peptides by simple chemical synthesis. And two amino acids, photoleucine and photomethionine, are special cases because they have so close structure to natural amino acids that they can be consumed by cells during biosynthesis of proteins, especially when we are talking about bacteria cells. So bacteria can produce proteins with structure close to natural with a photosensitive group inside. And also we have some artificial amino acids, which you can see at the right column. It should be mentioned that all amino acids are available in different forms. They are available as hydrochloride salts as well as protected forms like BOC, MOC, carbamide protected, or ester protected. I show a great variety of building blocks, and for convenience, if you are interested in those blocks, you can go to our special section at Enamine store. Let's look onto it. Here we have categories, which Alexei have shown before. Next, go to reagents for chemical biology and photo-labeling compounds. And all those compounds are categorized, and you can find by simple filters all available compounds. It should be mentioned that all building blocks about which we have spoken today are available in our stock. And in summary, what do we offer? We are a chemical company, so at first we offer building blocks for construction of photoaffinity labeling probes. You can purchase those building blocks and create your photoaffinity probes. Next, we provide synthesis of probes based on your design or based on our design based on your molecule. Both options are available. And in some difficult cases, when it's not easy to create photoaffinity probes by modular approach, we also provide custom synthesis of photoaffinity labeling probes. For all those options, feel free to contact our sales department. And in some cases, we may be interested in scientific collaboration. That's it from my side. I thank you for your attention. Alexei, your turn.
Yeah, fantastic presentation. Thank you, Yevhen. It was really insightful. Okay, so we will be waiting for the questions, if so. But one question I have from my side is in regards to whether it was possible to identify a binding site with BAL.
Thank you for question, Alexei. The short answer, yes, it is. The longer version,
Mhm.
to achieve this goal, you need not just a photoaffinity labeling probe, but you need also purified protein. In the case you have purified protein, you can conduct photoaffinity labeling experiment. So you can incubate your probe with your protein, irradiate it, and then you can digest obtained adduct to smaller peptide sequences, and you can analyze those peptide sequences by mass spectrometry. And you also can compare this data with data from digested natural protein, which hasn't been affected by your probe. And from those data, you can conclude to which peptide sequences your probe has been attached. But you
Mhm.
should be careful because such data is non-direct method, so you should use it as a preliminary data.
Okay, thank you. I can see that there is a question, another question in regards to the nature of the compounds that you were covering. Is it safe? Is it in general? Is it safe to work with diazirines? I
I
expect
understand
that
your
they.
questions. Diazirines are nitrogen-enriched compounds, and nitrogen-enriched compounds often are um, rich by energy. But according to our experience, alkyl, dialkyl, and aryl diazirines are completely safe to work with. Uh, Nevertheless, our chemists produce such building blocks in multigram scales, and we haven't had accidents by working with alkyl and aryl diazirines. It should be noted that we don't mention heterosubstituted diazirines. So when we are talking about alkyl and aryl compounds, they are safe to work with. But we always advise you to use all essential safety equipment, at least safety glasses, avoid direct sunlight, and avoid excessive heating.
Mhm. Yeah, as all the organic compounds, yes, to be stored accordingly. Thank you, Evgen. There is a question, another question from the audience. Do we offer custom synthesis of photoaffinity probes tailored to a specific protein target, or is the service limited to the catalog compounds only? So, do we have a list of make-on-demand photoaffinity compounds? I will rephrase the question, or we just have. I'm sure we do. We do have the catalog of those.
Uh, some compounds can be found in our real base, but as I
Hmm.
understood the question, whether we provide a, uh, looking for a search for proper probes according to specific proteins. Um, if we are talking about known proteins with known binding, with no affected uh, molecules, we can provide the synthesis of the probes. But when we are talking about unknown proteins and unknown binding sites, it's better to work with some scaffold, some bioactive compounds provided by our customer, and we can perform the synthesis of the probes based on those molecules.
Great, thank you. Another question. We have so many questions, which is good. It's always have to. It means that people are interested in the topic. So, what about the membrane bound proteins that cannot be easily purified or isolated without stabilizing membranes?
We can conduct them. We can
Hmm.
conduct experiments with those proteins, but we cannot identify binding site in those proteins. But let me return to the beginning. You can conduct a photoaffinity experiment with a natural cell. So it's not always necessary to have purified proteins. For identification of target molecules, you can use unpurified substrates.
Hmm. Thank you, Ken. Another question. Is it enough to synthesize one BAL probe per molecule?
It's a
or
brilliant question. Thank you. It's better to show. Um,
we have additional
uh,
slides? Nice.
mhm. I expected this question. So, at the beginning of the presentation, I told that during design of PAL probe, we should keep the structure of probe so close to starting structure as it possible. Because in the case we have no appropriate data about structure activity relationship, it's difficult to tell which part of the molecule is crucial for binding. So in the case we don't know which parts can be affected and which cannot be during PAL probe construction, we should test several options. Let's look at the screen. For example, if we have some bioactive compound 81, we can uh, design at least 4 probes. We can easily exchange amido fragment to amido fragment with diazirine fully functionalized moiety. We can exchange alkyl substituent at the pyrazole nitrogen to fully functionalized compound. And we can use smaller molecule approach and create probes like 84 and 85. And we should expect that binding ability of those probes will be reduced comparable to starting molecule. Nevertheless, we also expect that some of those probes will retain the binding ability, and in this way we will be providing with necessary data about binding of other molecules. So in general, we should synthesize at least 2 or better several probes with different substitution pattern.
Mhm. Yeah, thank you. Very, very informative. Informative. Well, probably the last question for today's session would be, can you list any any other classes of substances which are used for PAL? Another class.
Thank you for
So
question.
not the diazirines. Yeah.
Thank you for question. As I mentioned about before, chemists develop new classes which can be used for PAL each year. So among some newer classes of compounds, they are known acyl silanes, isoxazoles, sulfonyl hydrazones, and others. And those compounds are newer and there are not big data about their utilization, but there are several research papers on each class. So let's go over each of them. For example, acyl silanes are complementary compounds to diazirines because they have the same irradiation wavelengths, the similar radiation wavelengths, and they also generate carbons during irradiation. So they can be complementary to diazirines. Isoxazoles are rarely used as an additional blocks for PAL probe construction. Nevertheless, uh, isoxazole ring is known pharmacophore, and if you have isoxazole inside a structure of your studied molecule, you can use it without any additional groups. And sulfonyl hydrazones are easily accessible compounds in many cases, and the big advantage is their long wavelengths of radiation to be activated. But before, during presentation, I told about those compounds about which we know a lot, and there are a lot of data about utilization of diazirines, rhylazides, benzophenones as well.
Yeah. Thank you. It's a great field and it's expanding and work in progress. A bright future of this stuff is going, which is good. I think it would be it for today because we do not have any additional questions. But yeah, just for the information of the participants, you can always reach out to myself or to Yevgen via email or via LinkedIn. Yeah, we're always online. So if you have anything, or you can use the contact form on the website on enamine.net or enaminestore.com. So you are always welcome to pass the questions to the related to the topic or the related, not related topics. Yeah, yeah, thank you very much again. It was a great presentation. It's a fantastic field, and it's a great. It's very good that we are contributing to the global scientific community with these types of compounds. Yeah, and we are here. We're scientists doing uh, helping other scientists to to reach new horizons.
I agree with you,
Yeah,
Alexei. Thank you for your work, and dear guests, thank you for your attention.
yeah. Thank you for your attention, and please do not hesitate to subscribe to our social media. And yeah, looking forward to meeting all of you in Riga later this year on 20th of September. Yeah, so have a great rest of the day. It was a pleasure of ours, and take care, and everything is gonna be all right. With that, I would like to close the webinar. Goodbye, everyone.
Thank you. Goodbye.